In this video, we're going to talk through the notes for section 4.5, cooling of a sphere. So in this section, we're going to consider a sphere of fixed radius. We'll call it pi just for convenience. We wish to describe the temperature at time t in the sphere under certain assumptions. The temperature at time t we're going to assume depends only on the distance from the center. That is, u is equal to a function of rho and t, where rho is the distance from the center. So rho is between 0 and pi because the radius of the sphere is pi. And t is the time that's passed. So we're assuming that the temperature is just a function of the distance from the center, rho, and the time, t. So that's our first assumption. The second assumption is that the temperature on the boundary is held at a constant temperature of 0. So that is, u at pi comma t is equal to 0 for all t greater than 0. The idea here is that we're imagining that we have a sphere with some initial temperature, and we're holding the surface of the sphere at a constant temperature of 0. And so we want to know how the sphere cools over time. Assuming that the temperature is greater than 0, then it will slowly cool over time because the temperature at the boundary is being held constant at 0. So our third assumption is that the function u is bounded on the sphere, which seems like a reasonable assumption to make. 4, the initial temperature is constant throughout the sphere. That is, u at rho comma t, well, t is equal to 0, so I almost said u at rho comma t, but t is equal to 0. We're looking at the initial temperature, so that's u at rho comma 0, and we're going to say that that is some constant temperature throughout the sphere, where t is some real number. You can imagine that it's a positive number, so that the temperature in the sphere is a positive number, and the sphere is then going to start cooling because of the temperature along the boundary. So the differential equation we use for this problem is the heat equation. U sub t equals k times the Laplacian of u, because we're in 3 dimensions. So the Laplacian in polar coordinates is given by this rather impressive equation, or rather impressive formula. This is, we didn't actually show this, but we discussed it in one of the earlier lectures, where this is the picture that describes the meaning of rho, phi, and theta. But we're going to assume that, or we already have assumed, that u is just a function of rho and t. So that means it doesn't depend on phi or theta. So every time that you see a derivative with respect to phi, you just end up with 0. So these terms just simply go away. And you're just left with these two terms right here. These two terms at the front. That's all that you're left with. Now this is a much simpler Laplacian to work with. So the differential equation we wish to solve takes on this form. And this is subject to certain boundary conditions. In particular, the boundary is constantly held at 0. What else do we know? We have an initial temperature as well, which is t sub 0 for all rho, no matter how far you are. Notice we're not including the boundary here. Suppose the solution to the differential equation has this form. So we're going to use separation of variables. So we're going to assume that u is a product of a function of rho times a function of t. So capital R times capital T. Under this assumption, the differential equation takes on this form. We replace the partial derivative of u with respect to t with r times t prime. And these partial derivatives with respect to rho turn into ordinary derivatives of capital R, as you can see here. So this is separable, and you can separate it, and you end up with this equation here. 1 over k times t prime over t equals r double prime plus 2 over rho times r prime over r. And then we set that equal to some separation constant minus lambda. So as usual, this gives us two ordinary differential equations. The first one is a first order differential equation, and we know that this has solutions of this form, which are exponential. So t is equal to some constant times e to the minus lambda kt, because it's first order. We know how to solve that. For 2, we have a singular differential equation. This might look difficult, but we can actually make a nice little change of variables. Let y equal rho times r, and then your differential equation becomes much nicer. If you compute y double prime, you have to use the product rule, but you end up with 2 times r prime plus rho r double prime, which notice is right here. That's this thing right here. So this becomes y double prime. And this thing right here, that's just lambda times y. So our differential equation becomes something that we've seen before, y double prime plus lambda y. So we know how to solve this. Now what are we assuming? Well, capital R needs to be bounded on the set from 0 to pi. And y over rho is bounded there. Now, let me just remind you what R is. So R is the function of rho, okay? And we're assuming that R is bounded because we want our temperature to be bounded. So R is a bounded function, and y, don't forget, y is rho times R. So y equals equals rho times R. So that means that R is equal to y over rho. So since R is bounded on the set from 0 to pi, that means y over rho is bounded. So that has certain implications. For one, it implies that any eigenvalues must be greater than or equal to 0. If lambda is less than 0, then y is exponential. And if y is exponential, then y over rho is unbounded as rho goes to 0, because the exponentials are going to 1 as rho goes to 0. So then you have something 1 divided by rho, where rho is going to 0, that'll be unbounded. So that means you end up with an unbounded solution if lambda is greater than 0. If lambda is less than 0. If lambda is less than 0, then y is exponential, and so y over rho is unbounded. On the other hand, if lambda is equal to 0, then that means y is linear, so we can write it as a rho plus p, and that means that y over rho is a plus b over rho. But again, this needs to be bounded, so the only way that can happen is if b is equal to 0. So that means that y is equal to rho times a. But now we use our boundary condition. So we know that r at pi is equal to 0, and y at pi is equal to pi times r at pi equals 0. So what does that tell you? That tells you that y of pi is equal to 0. So y of pi is a times pi, but that's equal to 0. So that can only happen if a is equal to 0. So what that means is that you can't have lambda equal to 0. So as a consequence, lambda must be positive. So any eigenvalues must be positive. Consequently, we have that y is equal to an arbitrary linear combination of cosines and sines. So y is equal to a times cosine of rho times the square root of lambda plus b times sine evaluated at rho times the square root of lambda. Now again, we're looking at the condition that y over rho is a bounded function. So y over rho is bounded. Well, what does that tell you? Well, that tells you that a has to be equal to 0, because otherwise, it's just like with the exponentials. Y over rho is a times cosine of rho square root of lambda over rho plus b times sine of rho square root of lambda over rho. Let me just fix my lambda there. Now what do we know about this? Well, as rho goes to 0, this term is finite, but this term it goes off to infinity as rho approaches infinity as rho approaches 0 from the positive side. which it is, because rho is the distance from the origin. So as rho is approaching 0 from the positive side, this thing is blowing up. So that means in order for y over rho to be bounded, a has to equal 0. So that means that y is equal to b times sine of rho times the square root of lambda. We know that this limit exists as rho goes to 0. So this is finite. So that means y is equal to b times sine of rho square root of lambda. However, we know something in addition to this, which is we have a boundary condition. Y at pi is equal to 0. And this is really why we picked our radius to be pi, so it would make these computations nice. So y at pi is b times sine of pi times the square root of lambda. And that's got to be equal to 0. So that means the square root of lambda must be an integer. In fact, it must be a positive integer. So square root of lambda is equal to n for some natural number n, or lambda is equal to n squared. So that means we have an eigenvalue lambda equals n squared for each n and n. So we have our sequence of eigenvalues. So for each n and n, we have an eigenvalue lambda equals n squared, lambda sub n equals n squared, and the corresponding eigenfunction is 1 over rho times sine of rho times n. Now we already saw what t was. T was this exponential e to the minus lambda kn, but now we know what lambda is. So that means for each n we get a t sub n, which we call c sub n times e to the minus n squared k over t. This is just e to the minus lambda kt, it's just we know what lambda is now. So we want to let u be an arbitrary linear combination. So this is tn times rn, and we have this arbitrary coefficient cn in front. So this gives us our u. U is it satisfies the differential equation and the boundary conditions, but we have to make sure that it satisfies the initial conditions as well. So we need that u at rho comma 0 is equal to t sub 0. That's our initial condition. So if you compute u at rho comma 0, this is u at rho comma t. So we're looking at t equals 0. That just gets rid of the exponential. So you're left with the sum n equals 1 to infinity of cn times 1 over rho times sine of rho n. But this has to equal t sub 0. So multiply both sides by rho to get this expression here. And so now we can see that we have a Fourier series, a Fourier sine series. So that means that the coefficients here, cn, are obtained by integrating with respect to sine terms. So the integral, so c sub n is equal to 2 over pi times the integral from 0 to pi of our initial function here. So this is our initial function. So this t0p, that's that right there. So what we've just done is we've written our initial function t0 times rho as a sine series, a Fourier sine series. So in order to pick off the coefficients, we need to integrate this term against sines. So we're integrating t0 rho times sine of rho n d rho. And so of course we have the 2 over pi times the integral from 0 to pi of this. We can actually compute this using integration by parts. And I won't go through the details, they're here. I won't go through the details, but you can show that Cn is equal to minus 1 to the n plus 1 minus 1 to the n plus 1 times 2 t sub 0 over n. So here are the computations right here. So that tells you what Cn is. And that tells you what the solution is. So u at rho comma t is the sum n equals 1 to infinity of c sub n, which is right here, times the exponential, which is right there, e to the minus n squared k over t, times this sine n rho over rho term. And that gives you the solution for the problem of the cooling sphere.